Thanks. Today I will talk about noise population recovery from unknown noise. This is a joint work with Shaha Loat. Okay, let's first introduce the model. We just introduced the model. Is that so? In this problem, we are focusing on the learning from noise distributions. Let's say we have an original distribution pi. So this is a clean distribution, and say we get samples from pi. And also we do have another noise. Noise is have another noise mu. Say so the noise distribution is just somehow combination of pi and mu. So a general question is that could we recover pi with samples from noise samples? This is a general question. And in this work, we're focused on the Boolean strings, such like the previous talk. Okay, we can make our problems more specific, and we can give the definition of the model. Okay, let's say pi is an unknown distribution over Boolean strings with support v, and let's say mu is a vector of unknown noise parameters. Okay, in this talk here is that the mu is a vector of unknown noise. In all of the previous results, all of the algorithm assumes that the noise are known. So that is different. So the noise distribution is defined as follows. Say, we first sample a string according to the pi, and then for each coordinate, we are going to flip it with flipped independently with probability mu I. Say the goal is to recover the distribution pi from noisy samples. Say we are going to find a tilde pi such that the L infinity distance between pi and tilde pi is small. Okay, there is one more general question is the learning mixture of product binomial distributions. Okay, this is just much more general framework. Say this problem is defined in this way. Say we have pi 1 to pi k product distributions, and say where pi is the mixture of them with weights C1 to Ck. Then could we recover the parameters from the mixture distribution? Okay, this is a more general question, and say noise population recovery is a special case of this problem. Say we can given the following simple induction, following reduction is say if we have so if you have a noise distribution sigma pi mu, and say we can define a mixture of product binomial distributions easily. Say for each vi, we in the support set we define pi is equal to vi plus the noise. Vi is a fixed string, and vi plus noise is just the product distributions. So then we can mix them according to pi, and we get a mixture of product binomial distributions. Okay, this work is this problem is started by Feldman et al. In Folks 2005. Okay, record. So we're going to enumerate all of the current results. Say in the noise distribution and lossy distribution and the noise distribution with known noise, this problems has been well studied. And all of these problems, we have a polynomial algorithm now. But for the noise distribution with unknown noise, and even for the more general problem of learning mixture of binomial distributions, the best known result is still poly n over epsilon to the k to 3. So it is exponentially depends on k. So in our work here, we showed that noise distribution with unknown noise can be recovered in quasi-polynomial time. The dependencies depends on n over epsilon to the log k to the 1. So how could we do that? So somehow we use so our algorithm is close to previous algorithms by Wigderson and Yaldorf. Say we define identification in this way. Say this is also close to say let's v is a subset of Boolean strings, and small v is a string in this subset. Say for every s, we define IVS in this way. Say IVS is all of the strings in v such that VS means we're going to look at the s coordinates of the string v. Say Vs is equal to Us, which means V and U has the same patterns in the coordinate set S. So we say S is an identification if IVS is equal to V, which means we can identify the string V by these coordinates. So the set S is also called a teaching set of V. So because we can teach the V. Okay, there is a simple claim here is that, say, if we have for set V of set K, there is always a vector that has identification with size log K. Okay, this is an important lemma. Let's say we have a pi is an unknown distribution, and we can recover pi from the noise distribution in time mu 2 minus n. Notice that this is exponentially depends on n. So, but we can always do that. So now the idea of W. White's algorithm is simple. Is very nice, and now so it also uses another dimension reduction. Is that we can always assume that the support set V is known. So if V is known, then it's somehow the W. White algorithm somehow like a recursive teaching approach. So in the first step, we're going to choose a V that has short ID, very short ID. Then we can recover the marginal distribution pi s over these coordinates. Notice that now, apply the previous lemma, we can recover the marginal distribution by mu 2 minus size s. Say if we have s is log k, then we can recover it in mu 2 minus log k. Then somehow we can recover pi v because S is the identification of v. We can identify this. We can identify the vector v by the set S, and then we can just remove v from capital V, and then we'll go back to 1 and run this algorithm again. Okay, in this paper we show that even though in the algorithm here it assumes the noise parameters are known. In this work we show that we do not really need these parameters. In this algorithm we can show that we can also solve this question in coarse polynomial time without taking noise parameters as input. Okay, so basically we show that W-White's algorithm is robust. Say, let mu pi be approximate noise parameters such that the L infinity noise, L infinity norm between mu and mu pi is small, then we can still recover the distribution while taking mu pi as noise parameter. So there is a now there is a naive approach here is that we can just grid enumerate all of the parameters with step length k over with step roughly delta, and then we can run W algorithm for each candidate, and then we can recover a list of candidates. So, but the problem here is that there are n noise parameters. So if we want to enumerate all of the parameters, there are n tuta, there are delta tuta minus n potential candidates. But we show that we just need to enumerate log k noise parameters, then we can recover all of the rest of the parameters. Okay, that's our algorithm. So there are also another open problems which are interesting. So the first one is, could we use this approach to learn general mixture problems fast, as we mentioned. So in that problem, the best algorithm is still exponentially in k. So could we solve the problems much faster? Say, for example, polynomial in k and 1 over epsilon. And also, then how about the Gaussian distribution? It's also interesting to study the case that in the Gaussian distribution. So in here, we are studying the Bernoulli distribution. Okay, thanks.
Okay, questions? So I have one question. So what was your final complexity? What was your final complexity of your algorithm?
It's just final complexity is n tuta k log k tuta 3. Say n tuta log k tuta 3.
And does it depend on any parameters of the noise distribution mu?
We assume that mu is upper bounded by a constant. Say we assume mu is a constant.
Okay.
Yeah.
Thanks.
Yeah,
Let's thank the speaker again.